So any questions? None. So the ID function and everything connected to it is clear? Or why do we need the ID function in the first place? Is that clear? Let me just remind you that last day what we actually talked about was this. The Wkb approximation or the Jwkb approximation for a wave function. Okay, this is, okay, it's wrong to say this is an approximation. After all, this is the Wkb wave function, which is an approximation to the actual wave function. So this is where you stop after taking the first two terms, the zeroth and the first order term in the Wkb series, and you end up with this result. Oh, thanks, Barnali. I forgot presenting. Okay, so this is basically the Wkb approximation, which is an approximation to the actual wave function, but this is given by this term. You take the zeroth and the first order terms in the series that you developed in powers of h cross, and then you end up with this result. And this result works well whenever the potential is slowly varying. And basically, the condition for slowly varying essentially when something like actually m times f by p cube has to be small. This is the condition. And this essentially is a condition which is derived by using the fact that after all we had a power series in h cross and we stopped at the first power. So we are actually saying that the second order term, the one we ignored, is very much smaller compared to the first order term, the one we kept. And if you do that, you end up with this result where you can see the potential has to be slowly varying because the derivative of the potential with position is of course the force F here. But what is important is just F being small is not really the point. F by P cube is important. And that means that when you're close to a turning point where P is nearly zero, of course, when I say turning point, I mean the classical turning point, a point which classical mechanics would have insisted your particle would turn back from. Of course, at that point, P vanishes. When you get close to a turning point, P is very small. So even if the potential were very slowly varying, close to the turning point, the Wkb approximation definitely breaks down. And that is sort of obvious even from the Wkb expression itself, because if you see, you have a phase term which essentially looks like a to the power I by h cross p times x, except that now that p, the momentum is varying with position because the potential energy is changing. Instead of taking p times x, you do p of x prime dx prime integral. That is fine. There are no problems there. But you also have an extra factor, overall factor, which is inversely proportional to the momentum. And that, of course, is a problem because when the potential energy becomes equal to the kinetic total energy, which means at the turning points, the denominator would vanish and the wave function would blow up. The actual wave function definitely never blows up. So what this is really telling you is that the approximation that you are using is fine as long as you're far away from turning points, but when you're close to a turning point, this approximation is bound to be a bad approximation. So if you have a situation like this, so you have x and this is, let's say I'm plotting potential here, let's say the potential is in red, something like this, and let's say the total energy, the line in blue. is this one. Then in this region, WKB would work fine and tell you that you have a sinusoidal wave function. Of course, the wave function will have varying wavelength. As you get closer and closer to this side, the wavelength is going to keep on increasing simply because the momentum keeps on decreasing. So you will have a wave function which sort of looks like this with the wavelength increasing. Okay, maybe I will just try drawing it a bit better. Say you might have a situation like this. Now, on the other hand, on this side, you would expect exponentially decaying solutions. And that is also something the WKB solution will tell you. Because WKB will tell you that when in the classically forbidden region, where the total energy is less than the potential energy, E minus Vx is negative. And so this thing is purely imaginary. And okay, to be more precise, very precise, you should have a plus or minus sign here because you could have waves going in both directions. Here, what you would have is a superposition of a decreasing term and an increasing term. And of course, since this region goes off all the way to infinity, you will expect a decreasing term. Now, this decreasing term, of course, will have different values of the decrease the constant in front of the x as you move further and further out, because this will keep on changing. And the same will happen on this side. So as we were saying earlier, the real issue is in the immediate vicinity of the turning point, the Wkb approximation breaks down. Everywhere else, it's a pretty good approximation. But as we talked about the other day, this makes it very difficult to actually use it in the standard sense, because when you do things like solving problems with say with a barrier or a square well or something like that, we have three regions where we know the solutions, and we know the solutions all the way inside the region. So when you're solving a problem like this, say, and you're trying to, so this is, if this is your potential and you're trying to find out the energy eigenvalues and eigenfunctions, you know exactly what the solution is here. You know exactly what the solution is here. And similarly, you know exactly what the solution is on this side, and all the way right up to the boundary. And so now all the job that is left is you need to match the solutions at the boundary, and then you have an actual solution. That cannot be used here for the simple reason that here we know the solution in this region, in this region, in this region, we actually have pretty good approximation to a solution in these three regions. But when you're close to the turning point, of course, I've shown this in a vastly exaggerated scale. Close to the turning point might even mean a very narrow region like this. But when you're close to the turning point, your Wkb approximation definitely breaks down. And so you definitely cannot match the solutions on the three sides. And then what we said was, okay, what we will do is we will exactly solve the solution, solve the wave function in the immediate vicinity of this region. So in the immediate vicinity of the turning point, the potential looks like a straight line. So I can actually find out the exact solution to the wave function, exact within quotes after all. But remember, I've already made an approximation here. I'm approximating the potential in the immediate vicinity of the turning point by a straight line potential. Within the context of that approximation, I have an exact solution, which is via Airy's equation. So I know the solution is like basically the Airy function. And what I need to do is be able to match the Airy function behavior, the actual Airy function, which is the actual solution to this problem here. We need to match it to this Wkb solution on this side and the Wkb solution available on this side. Once we manage to do that, let me just get rid of the shading first. So we have a solution here, which is something we exactly know. because we know what the area function behaves like. And then using the fact that the area function will match the WKB solutions on both sides, after that I can simply forget about the area solution. I will say, okay, I have a WKB solution on this side with this coefficient, on that side with that coefficient, and the coefficients have to be related in this particular manner, so that the solution will match up neatly inside. Of course, we are not claiming that that this solution and this one actually matches up, because these solutions are not even accurate when you get close to where you need to match them up. But you have an area function solution which essentially matches this one and this one. And once you have done that, your job is over. And then you can sort of forget about the area function in between. I can directly use the connection formula. So are there any questions about this much so far? Or is this clear? This is the basic idea behind the connection formula in the WKB methods. The rest is maths. The maths is not very simple. Okay, let me warn you that. But frankly, you can use a WKB method just sort of like a rule. You don't even need to know what the area function asymptotics are, which actually gives you the connection formula. Of course, you need to know that. That is, it's an important part of your derivation. But when you're applying the thing, you don't really need to go back to the derivation every time. But the basic idea has to be understood properly. Is there any confusion with that? If so, I can of course explain again. But let me know that. If you think it's okay, then it's fine. I can move on to the math part of it, that is the actual area function behavior. How do we know the energy E? Or are we not? What? Sorry. Let me just check. Or are we not dealing with stationary states only? Well, actually, no. We are dealing with not only stationary states, we are dealing also with scattering states here. That is, tunneling problems, for example, can be solved by the same method. But all of these are energy eigenstates. That way is true. Of course, so what the point is, how do we find out energy in the, say, in the square well case? If we assume that the energy is just any value, then these solutions will not match, right? Then the exact solutions I know in these three regions will not match in their value and in the derivative at the boundary. In fact, the way in which we solve these problems is that we find out the quantization of energy by actually matching the solution at the boundaries. Of course, the real point is the matching this solution is possible only at certain values of energy and not at other values of energy, at least for bound states. Basically because of the fact that we have already taken the boundedness of the wave function into account. Remember, on this side, you actually had an exponential solution, which could be a decaying exponential, also a growing exponential. We started out by throwing away the expanding or the increasing exponential, right? Because we knew the solution has to stay well behaved over the entire real line, and an increasing exponential cannot be a solution where in a region where plus infinity is in the region. So you have already chosen boundedness, and after you choose that, the only thing that is left is continuity and derivative continuity. That is for this particular problem. Here, basically the same thing. You will find that the connection formula cannot be satisfied. That is, the connection formula meaning the ratio between the WKB solution here and the WKB solution here. That's fixed by this interpolating area functions behavior. But you also have a similar thing on this side. And after all, the point is an exponential decaying solution on this side, or at least something which is approximately like an exponential decaying solution on this side, will predict that there will be some amplitude on this side. But this one will also predict some other amplitude, right? And these two amplitudes have to agree, because now you're talking of the wave function in the same region. And because if you have multiple turning points, the predictions that you make about the wave function from those multiple turning points and the connection formula that we are going to derive They have to agree with each other, and that is what gives you energy quantization. Because if you chose some other value of the energy, then whatever this wave function continued on this side would say would not agree with whatever this wave function continued on this side says, and then you're in trouble. So that's how energy quantization follows. In fact, one of the immediate consequences of the WKB method is that it gives you a result which is very, very similar to this one. Does anybody remember what this is? If you have a periodic orbit and you integrate momentum times dx here, this is okay. What is the quantity on the left? This quantity is a classically important quantity. Does anybody remember what that is? Or you may have already done it in classical mechanics, or maybe this was not covered. This may not have been covered in your classical mechanics course, but this is actually called the action. And there's the action in the action angle variable formalism. I'm not sure whether that has been covered in your course. Bohr actually came up with this condition that the action for a cyclic process has to be an integer multiple of h. In fact, that's exactly what will follow from here. Not h, but nh. In fact, Bohr's condition is something which Bohr came up with on the basis of semi-classical arguments, arguing using Planck's principle and so on, but he did not really have a proof for this. One of the first things that WKB will do once we have the connection formulas in hand is that it will tell you that this is a semi-classical formula you can use for the energy to figure out energy quantization. It's called the Bohr-Sommerfeld quantization principle, and the WKB essentially gives us a justification for that, with some small modification, but it essentially justifies what Bohr did primarily on heuristic grounds long ago, long before quantum mechanics came into being. Okay, so next, what we will need to do is, now that, okay, this part is the physics. That is, you have solutions in different regions, you need to smoothly join them together. In the immediate vicinity of the turning points, these solutions that you have, these approximate solutions break down, but there, thankfully, you actually have exact solutions which you can use. And then you're basically matching, you're not really matching the WKB solution here with the WKB solution here. You're matching the WKB solution here with the asymptotic behavior of the ID equation solution here. And then you are matching the asymptotic behavior of the ID solution here to the WKB solution on this side. And in the process, ending up matching the solution here to the solution here. Okay? And this is the basic idea. The rest, of course, is the maths which you need to work out in order to understand the asymptotic behavior of the WKB, of the Airy equation solution. That is, what does the Airy function AIX and BIX behave like when you are very far away from x equal to 0 on both positive and negative sides. Okay. So the last day we talked about a contour integral version of the solution to the Airy equation. Is there any confusion about that? That's a by the way, that's a very, very important method, because not only the ID equation, but most of the special functions that you deal with actually can be solved using this procedure. And many of the properties for, say, the Hermite polynomials, etc., that we actually derive using some other method can actually be derived rather nicely using this integral transform method. And many properties, including the generating function, can essentially be derived out of this method. So this method itself is of more importance than just the WKB application, being something you need in WKB. Okay. Of course, when you're doing WKB, what you really need is a solution to the ID differential equation. But this method is actually pretty universal. It can be used in many, many different situations. So what we did essentially was ask for a solution u of x, or actually we moved on to the complex plane and said, okay, let's solve this in the complex plane by taking sorry, by starting with from this some function x of z which you need to find out, and we figured the whole thing out and ended up with this result that the ideal equation has this solution. This essentially is a Laplace transform method. So basically what you end up with is this result. It's a minus t cubed by 3 plus zt dt over some contour. And the important thing is this contour cannot be completely arbitrary, because in the process of going from the differential equation to this integral form, we had made an assumption that essentially this integrand is going to either repeat at the two endpoints of the contour or vanish at the two endpoints of the contour. So that puts an important restriction on the contour that you can choose. And what we figured out in the last class was this, that the contour that you could choose would have to extend all the way up to infinity, because that's the only way can make this function vanish. Okay? But then the problem is, because you're dealing with t cube, and it is a minus t cubed by 3 may not actually vanish as t goes to infinity, unless you're going in some restricted regions. So what we figured out there was this, that let me try drawing this as neatly as I can, and I'll step at the very beginning. So this is one region. So basically what we are saying is you're allowed to go off to infinity either in this region or in this region or in this region. So what parts are forbidden are these. Let me just shade them first. Oops. So this region is forbidden. This region is forbidden. And this region is forbidden. You're allowed to go off to infinity either along this. Let me just. So either in this sector or in this sector or in this sector, because those are the regions where as t moves off to infinity, it is a minus t cubed by 3 is going to die down to 0. So is this part clear to everybody? If you have any questions about this, this is the really tricky part of this whole calculation. Everything else is pretty straightforward. Yes? So this is okay with everybody, I am assuming, because nobody is saying no. Okay, let me. So you're not allowed to go here. You are allowed to go here in between. You don't have to avoid this region forever. It's only that when you're going away all the way to infinity, you're not allowed to go into either this sector or this one or this one. You're only allowed to go through these unshaded regions. So what we had is this. You could have a contour. Oops. It starts here, goes here. So let's call that C1. Could have a contour which goes like this, C2. Or you could have a contour which goes like this, which is C3. And so basically we have our solution essentially reads like this. And as we talked about at the end of the last class, you cannot really have three independent solutions to a second order differential equation, and you don't. These are not three independent solutions. There are only two independent solutions here. Why? Because can anybody tell me why this is true? Yes? I hope I'm still connected. Now I'm starting to feel I'm not connected. I am connected, it seems. So is this okay? So can anybody explain why this is true? IC1 plus IC2 equals IC3. Yes? I may even have made a mistake. We can express any one of the solutions in terms of the other two, hence that's true, but that's my claim. That was not the point. The point is, this is, of course, this statement really is saying that we can express any two of the any one in terms of the other two. Right? That means the three are not independent. So it's just two independent solutions. Say IC1 and IC2 are two independent solutions. IC3 is not. I agree. My question is, can anybody see why this is correct? IC1 plus IC2 is IC3. Why is that the case? Let me just remind you, this is what C1 is for this contour. This is in, of course, in the context of this particular integrand. If you are using this particular integrand, which you have to, if you want to get a solution of either ID equation, then IC1 plus IC2 must be equal to IC3. Question is why? Okay, so I've already got two answers in the chat, and both of them are correct. Although Herschel, actually, you didn't really need the additional condition. The function is an entire function, that is enough, because if you take the contour formed by C1, C2, and minus C3, that is, of course, you might say C2 may go off to some point at infinity, and C3 may not go to the same point. C3 may go to some other point at infinity. But frankly, now, of course, the other issue, since the integrand vanishes exponentially rapidly, whenever you're going to infinity inside this region, then you can always add up an additional piece of the contour which will contribute nothing. And then what you can always do is get a contour like this, a closed contour, which goes like this, then along some infinitely far away strip, then along C2, then again along some infinitely far away strip, then again C3 and come back. So you basically have 6 pieces here, C1, C2, C3, and these 3 joining pieces. The joining pieces contribute nothing, and C3 is being traversed in the opposite direction. So it's actually IC1 plus IC2 minus IC3. And this quantity has to be 0 by the Cauchy theorem, simply because you are integrating a function which has no singularities. And if you integrate an analytic function, which is analytic everywhere here, so it's an entire function all the way. So, okay, Swandan has also said basically C1 plus C2 minus C3 is a sort of closed loop. And hence the integral is 0, of course, but also because of the possible of this behavior of the integrand. If the integrand had not been an entire function, had poles in between, then this would not have happened. Okay? Clear? So basically, the C1, C2, and minus C3 forms, along with these additional segments which you can throw in for free because they don't contribute anything, you now have a closed loop, and integrating an analytic function in a closed contour gives you 0. That's Cauchy's theorem. From that everything else follows, right? So what we have is IC1, IC2, and IC3 are not independent. Only 2 of them are, and hence you can define the solutions to the ID equation using any 2 of these contours, and they will be independent solutions. In fact, the definitions that are given are these 2 solutions that we have already seen before. AI, okay, let's call it AI. Let's put an X here. This X can also be complex, but for the timing, that's not important. So AIX is by definition so when you integrate along this particular contour, okay, what's the special thing about this contour? It has to begin somewhere in this sector. That is, of course, this is 30 degrees, 90, 180, and an additional 30. So starts at 210 degree, goes all the way up to 270. That's a bad way to put things. You should, of course, always be using radians. But basically, it has to start infinitely far away, somewhere whose phase angle is between 210 to 270, and end up infinitely far away, somewhere where it is where the phase angle is between 90 degrees and 150 degrees. That gives you C1. The exact shape of the contour C1 does not matter. The contour C1 can simply be something as weird as this. All that matters is when it goes off to infinity on both sides, starting in this sector and ending there. That's what gives you C1. And notice that my original red curve and this weird blue curve, both will give you exactly the same value for the contour integral. And that is something you already know, right? You can deform a contour as long as you do not cross any singularities. And here there are no singularities to cross. So any such contour will be C1, and integral over C1 of this integrand to the minus t cubed by 3 plus xt is exactly what is defined to be the first airy function AI. And BI has a slightly different definition. Okay, different, of course it's different, but what it is defined to be is 1 by 2 pi Notice that there is an I in this definition, there is no I here. And that is essential to ensure that your solutions AIX and BIX are real for real x. For that, you need this factor of I here. Okay. So basically, once you have this, you can use it to derive various important results, various kinds of results. For example, so instead of using this contour C1 to define AIX, I could use a contour like this. Let's see. Let me just use some other color, maybe this one. What we could do is actually use a contour which is like this, right? Because it starts in the right sector, goes off in the right sector. Correct sector, I mean. Okay. And then I can keep on moving this purple line closer and closer to the imaginary axis. And ultimately, you can exactly coincide with the imaginary axis all the way from minus infinity to plus infinity, just ensuring that you have a slight shade of touch of, real part which is slightly negative for t, right? You're not moving exactly along the imaginary axis, you're just moving slightly inside the imaginary axis. If you do that, that's also an identical contour. And so you also get the same integral. So, for example, you can easily see that IC1. Now, notice that what you're really doing is this. You're taking, this is the integral you need to do. It is a minus t cubed by 3 plus xt. But you're moving along the imaginary axis from minus I infinity to plus I infinity. And so if you use, instead of t, if you just use I tau, then what happens? The limit for tau becomes minus infinity to plus infinity, right? Because that contour is going from minus I times infinity to plus I times infinity, plus a very tiny negative real part. So that very tiny negative real part, we can easily take the limit as that tiny negative real part goes to 0. And I'm writing that limiting expression here. There's minus infinity to plus infinity of this expression, e to the power minus t cubed by 3. Now t is I tau. So okay, anything else do I need to put in? Is this correct or do I need to put in something else? An extra I, exactly. Because dt of course has an extra I. Let's just check everything. Or is this correct? I've deliberately made a mistake somewhere here. You should be able to spot that. Okay, let me just show you these two things side by side. This was the original integral that we needed to do. All I've done is change your contour so that it moves exactly along the negative imaginary along the imaginary axis, and this is what I claim the integral has become. The exponential will have, okay, you mean plus I tau cubed by 3, right? Of course, because you already had it is a minus t cubed by 3, but now I put in t equal to I tau, so I cube is minus I. You have to use that. That's it. That's all that you need. And then it's very easy to see that this is twice I, integral from 0 to infinity. By the way, this is not an even function, right? Is it an even function or an odd function? Yes? What is it? Is it even or odd? Whenever you have an integral from minus infinity to plus or minus a to plus a, it would be nice if you had an even or an odd function, right? Yes? Come on. When I say even or odd, of course, I mean even or odd function of tau, the integration variable. Is it even or is it odd? It's neither, of course. It's neither even nor odd. The exponent in the exponential is actually an odd function, but the exponential is neither even nor odd. But every function can be written down as a sum of an even part and an odd part, correct? And when you're integrating this from between symmetric limits, the odd part will definitely give you 0, and the even part will be the only part which survives. So what we can write this integral as is an integral from 0 to infinity of twice I. The 2 comes in because the even part contributes twice of the even part of this. But what is the even part of this? Yes? The even part of this is a function which all of you know very okay, is cosine. Exactly. Just use Euler formula or whatever you call it, e to the I theta, cos theta plus I sin theta, and you end up with this result. That is, I hope I have managed to convince yourselves why AIX has this I in the denominator. It's 1 by 2 pi I times IC1, right? So this basically is 1 by pi times this integral. And what the good thing is, when x is real, then this cosine tau cube by 3 plus x tau, of course, is a real quantity from 0 to infinity, and its integral gives you what AIX is going to be. Okay? So, all the point I'm trying to make is the choice of 1 by 2 pi I as a multiplying factor for AI is actually not accidental. It has been done deliberately in order that you end up um, uh, with a real valued function for real arguments. You can easily convince yourselves that the definition for BIX without the I also gives you a function which is real for real values of x, following exactly the same procedure, except for one thing. The point is, what contour can I take here? I can't take a contour which goes like this, right? The contour I have to take there is something like this, something which goes along the negative imaginary axis. Say for C3, what we need to do is something which goes along the negative imaginary axis, goes very near the origin, then turns around. So basically, something which essentially bends. So something which goes like an L. And also, of course, for C2, what you need to do is okay. The point is, since you are free to bend your contours in any way you want, as long as you're dealing with entire functions, this kind of thing can be done. And once you do that, can easily change those integrals, which are integrals over complex contours, into real integrals and use them to figure out that both the airy functions AIX and BIX defined along those lines would essentially be the same thing. It would be real functions of x. Okay? Now, this is not the thing that we need really. We need asymptotic behavior. We need behavior when you are very, very far away. When x is very large, let's say. Okay? But this particular integral representation is good for many other things. For example, just the opposite extreme. When x is very small, can anybody tell me how I could use this integral to find out the behavior of the function AIX when x is very small? Or forget this one, just why not just use this one directly and try to figure out the behavior when x is very, very small. By the way, can anybody tell me what the value of this integral is when x is 0? This, of course, is the integral when x is 0. How can you find out its value? A clever choice of the contour would be nice. Can you choose a contour in such a way that this integral, remember this t is a complex number in general, right? And when you have complex numbers in the exponents, you may have wild fluctuations because of phase changes and so on. You want to avoid that. You would love to be able to use a contour, the one where the integrand is real throughout. Is that possible? Yes, can anybody tell me when is this contour real throughout? When is it is a minus t cube by 3 real? What does that tell you about t? If it is a minus t cube by 3 is real? Shayan is saying a V-shaped contour. Good. But not any V-shaped contour, right? Specific V-shaped contour. By the way, it's a minus t cube by 3 is real. Of course, that means t cube by 3 is real, right? Because if t cube by 3 had an imaginary part, that would, of course, give rise to an imaginary part in the corresponding exponential. So if this is real, what does it tell you about t? And let us go back to our original diagram, although this is now very cluttered. So what I will do is I will try removing, maybe, let's not remove the original C1, C2, C3 from this. Okay, Sharon is of course right in the sense that what he's saying is if t cube is real, then what you really need is start with the three cube roots of unity and multiply them by a real number. A real number cubed is always a real number and a cube root of unity. Of course, one of them is 1, that's real anyway, but the other two cube roots of unity, omega and omega square, when you cube them, you get a real number. So what you could do is start, so if you, now let's say you want a contour where the integrand is real throughout, okay? Now, for that, can anybody tell me what is the phase angle for omega and omega cube? In degrees, if not in radians? Then of course tell me in radians, that's fine. But what is the phase angle? In fact, radians is easier perhaps. I hope these are not unfamiliar things. Three cube roots of unity. So I'm asking for the argument of omega. How much is it? An argument of omega square. Okay, so Shayana said 2 pi by 3, 4 pi by 3. I'm pretty sure everybody knows this, right? Or just 1/3 of a full circle, full angle, 2/3 of a full angle. These are cube roots, right? So basically, if you take a contour which goes like this, remember we are dealing with a contour of type C1, so it has to start in this sector, so it has to go like this, making an angle 4 pi by 3, and then shoot off to infinity, making another angle which is 2 pi by 3. So this is this other angle is 4 pi by 3. So if you do that, then your integrand is real throughout on this contour. Okay, and then you can easily reduce that integration that I did to basically a gamma function integral, and you can easily figure out the answer. When I say you can easily figure out the answer, that of course is a big hint that you should figure out the answer for yourselves. All I'm saying is, all you need to do is, for this particular purpose, if you want to see what is the behavior, say at x equal to 0, the easiest thing to do would be to deform the contour until it becomes one over which the integrand is real throughout. And then that integration essentially becomes a trivial thing. Trivial in the sense that if you know the gamma functions, it's a trivial thing. And I hope everybody here knows the gamma functions. So that is, of course, what C1 is. What C2 would be like is back along this, and then here. C3 will be like this and this. And using these, you can find out not only AI and BI's behavior at x equal to 0, but more importantly, even what happens when x is close to 0 or for small values of x. And anybody tell me how? Suppose x is small, how would I go about finding out an approximation for ICI? Yes? By the way, just because this is complex analysis doesn't mean the rules of ordinary integration or ordinary maths have just suddenly disappeared. Aman is saying Taylor expansion of e to the xt. Of course. Why don't you just write e to the xt, this thing, as 1 plus xt plus x squared t squared by 3 factorial and so on. And do it exactly for this contour. So that e to the minus t cubed by 3 is real throughout. And for every term, you get essentially an exponential with some power of t times some power of t. And again, this will simply give you the gamma functions back. And what this actually does is not only gives you a expression for the Airy function for small x, it actually gives you a power series expansion of small x, right? Exponential as x, x squared, x cubed, and all such powers. The Airy function will simply have those powers of x multiplied by some integrals which can be evaluated using gamma functions, and this will give you the power series expansion for the Airy function AI. Also, if you did the same thing for C2 and C3, carefully of course, keeping the contours intact and then going in the right directions, you are going to get rather nice behavior. That is, you're going to end up with a power series solution. So you want the power series solution for the ID equation, you can start from this integral and find out the power series solutions. Okay, so that's another part of the job, but none of this is close to what I really want. What I really want is asymptotic behavior. What happens when x is very large, not what happens when x is very small. Okay. Now this is where a particular technique, which is of immense importance in many branches of mathematical physics, also just in pure maths as well, called the saddle point approximation technique comes in. Okay. And the basic idea behind the saddle point approximation technique is this. Okay, firstly, let me just get rid of the clutter here again. I will have to remember that you're not allowed to have here, here, and here. So I've got C1, C2, and C3, which I just erased. Okay, let me just forget about C2 and C3 for the time being, because I'm going to just, for the time being, I'm going to only talk about the AI function. The other the BI can also be handled in exactly the same manner. So what I need is this kind of contour. Now the basic idea behind the saddle point approximation is like this. You're exponentiating a function like this, right? This is your integral is an exponential. And you're free to distort your contour any way you want, as long as you keep the ending point within the end points within the correct sectors. And using that, what we will do is choose a particular contour which works best when x is very, very large. And how does that go? What you do is basically this. Take this function xt minus t cubed by 3, which is being exponentiated. Treat this as a function of t, because that's what you're really integrating here. And now extremize this. Find out the points where this is extremum. That is, just find out where the extremum occurs. Now, what is this? Of course, since you're exponentiating this function, where the exponential is an extremum, where the exponent is an extremum, the exponential will also be an extremum. So f prime t equal to 0 tells you where the integrand is largest or smallest. So what is this going to give you? This is going to give you x equal to t square. So this gives you a special value of t, say t0 equal to what? Is this correct? Does it give you t0 equal to root x? Plus minus. Good. So, but is that the only thing? Or is there something else that you have to also worry about? Tell me. Okay, Sharon has a very pertinent question, how to define maxima minima for complex functions. That is a pertinent question. And I deliberately did not answer that in the hope, or didn't even ask that in the hope that somebody would raise that question. We will answer that soon. But firstly, just tell me this. If x is t squared, does it tell you that t0 is plus minus root x? Yeah. Well, you may get away by saying this, but notice that this is strictly speaking correct only when x is positive. When x is negative, even then you do get some t0 value, because we are allowed to move over the entire complex plane. So what you get? Okay, so basically depending on whether x is positive or negative, you have your location for these special points. When x is positive, the special points are located, let's say, here at root x and here at minus root x. Okay. When x is negative, the special points are rooted here and here. Of course, these 4 points are not there at the same time. For positive x, you have these. For negative x, you have these. So maybe I should actually use different colors for these. For negative x, your special points occur on the imaginary axis. Now, a very important question is maxima minima for complex functions. What does this at all mean? Because a natural question would be, there is no sense to this maxima minima because there is no order among complex numbers. True. But let's say even for magnitude, can you talk about maxima minima for the magnitude of a complex function? Is that possible? Or the real part of a complex function, the imaginary part of a complex function, can we talk about the maxima minima there? Yes. Okay, you can talk about those things, but there's one very important thing. These are solutions. So the real part and imaginary part of a complex function satisfies the harmonic equation, right? D2 del 2u del x2 plus del 2u del y2 equals 0. And what does it tell you about the maxima minima of such a function? Yeah, no local maxima or minima exists for the simple reason the two second derivatives have to be of opposite sign. And because the two second derivatives are of the opposite sign, you cannot have any local maxima or minima. It can have a maximum in one direction, minimum in the other. You can have, basically you can have saddle points. You know what a saddle point is, right? A function of multiple variables can have maxima or minima definitely, but functions of this kind, solutions to the harmonic equation, or basically Laplace equation in 2 dimensions, cannot have local maxima minima. They can have saddle points. They can have maxima in one direction, minima in another. And it is this saddle, that is precisely why this technique that we are talking about is called the saddle point technique. Is a saddle behavior which is very, very important. So let us try to understand how, using the saddle point technique, we can actually get nice approximations to solutions. So let's just make a detour and talk about a slightly different kind of integral, where the saddle point method is very easy to understand. Let's say you have an integral which looks like this. You want this integral. Basically, you want to know the behavior of this integral for lambda going to infinity. That is when lambda is very, very large. Okay. Now, at least let's talk about the real case today. The complex case essentially will be part of the lectures, will also be part of the assignment. So for a real function case, of course, one important point to note is that you can perhaps have maxima minima in your function f of t. And here, if lambda is very large and large positive, can anybody tell me where will you get maximum contribution for this integral? So let us start with a situation where everything is real. So this contour C is also along the real line. Where would you get the maximum contribution? This f of t is completely arbitrary, but let's say f of t has some graph. Let's say it goes like this. Where would you get the maximum contribution for this as lambda becomes very large? So would the maximum contribution come from near A or near B? Or maybe near C or something? Well, let me even make it simpler. Okay, Anuruddha said from the maximum f of t. Of course, you will get contributions from each of the local in fact, you should get contributions from every point. However, because you're exponentiating the function with a positive, very large positive coefficient, lambda is very large and positive, you would expect most of the contribution to come from near this region, from near the global maximum. And there, this is basically the idea behind this method. What you do is you take this point, let's call the value of t here t0, near the global maximum. And what you can, of course, write is this f of t0 plus and now Okay, let's just say we will make our life a bit easier by absorbing lambda inside the definition of the function f of t. So from now on, whenever I say f of t, I really mean lambda times the original function f of t. So this function actually grows in size as lambda becomes very large. And now what you are going to say is this integral, which will be some real integral from alpha to beta, comes over some limits of e to the f of t dt. This f of t is not the same as that f of t. It has this extra lambda absorbed inside the definition. It's simply e to the ft0, which is a constant, so it can't come out of the integral. Because this is an approximation, there are other terms. By the way, this f double prime t0, what is the sign of this quantity? Yeah. Come on. F double prime t0, what is this? Positive, negative, what? Yes? I'm assuming it's taking time for you to type out because otherwise everybody should know the answer, right? The maximum. So what should the second derivative be close to it? I hope everybody realizes why you don't have the first derivative term and so on. The second derivative, of course, has to be negative. And what this shows is that this is basically like a Gaussian, apart from this e to the ft0, is like a Gaussian integral, right? Now you might argue that there are other terms which comes in, which are cubic order and so on, but basically way before you get that far away, the contribution only comes from close to the peak, because before, when you go very far away from the peak, the exponentials already decayed quite a lot. Okay, so since the contribution only comes from close to the peak, you only need small values of t minus t0 to worry about. But now that you have this, the idea is that I am actually integrating from alpha to beta, and the peak is somewhere here at t0. But do I really need to integrate this from alpha to beta, or can I just safely say that this can be expanded to minus infinity to plus infinity? Notice that this function dies out so rapidly with distance, especially remember f has already absorbed lambda in it. F double prime has also absorbed lambda in it, so f double prime is a huge number, huge negative number. That essentially means that the Gaussian has a very narrow width, especially in the limit as lambda goes to infinity. So what does this do? It essentially pulls down the exponential so fast from when you move away from the peak, then the fact that you're integrating from alpha to beta from over some finite interval does not really matter. You can equally well integrate from minus infinity to plus infinity. If you do that, no problem, because your integrand is nearly zero there anyway. Right? Since it has almost vanished there, you don't really care. Okay. But you all know what the integral is from minus infinity to plus infinity, right? Then it's just a plain Gaussian integral. Okay. So it's e to the ft0 times the value of this Gaussian integral. And what is that? So if f of t has this behavior, that it increases very rapidly with some parameter. Some parameter other than, it's not increasing with t, remember. There is some extra scale factor which makes the whole thing go up and down, maybe by having an extra factor outside, like when I wrote it as lambda f of t. Then the integral of an exponential can be easily approximated by the contribution very close to the global maximum. And all you need is the value of the derivative, value at the local maximum, and the value of the derivative at the local maximum to estimate what this integral is going to be. So this is basically the idea behind the saddle point method. This is not the saddle point method because here you're not using any saddle. Here you're doing real calculus, calculus on the real line, and you are just taking contributions from maximum. Okay? Is that clear to everybody? And have you seen this kind of calculation done anywhere, in any subject? Some function which becomes very, very large so that the contribution comes only from near the peak. Some exponentially large function which has a parameter which blows up or becomes very, very large. Actually, you have seen this quite often. And at least definitely in one subject, if in nowhere else. Delta function is, of course, delta function is not really the thing that I have in mind here, because the delta function actually blows up, right, but it doesn't, but it's zero everywhere else. So it's not a function which blows up overall with some other parameter. Remember, here I'm talking something like lambda times f of t. Well, so the function may be non-zero everywhere. When lambda increases, the whole thing increases. Contributions coming only from very close to the peak and almost no contributions anywhere else. This is something which I've used very, very often in some discipline of physics at least. Which is what? Okay, what is the kind of subject in physics where you get very, very large numbers? That should be a dead giveaway when I say that. Partition function in stat mech. Well, not just partition function, everything you do in stat mech. In fact, everything you do in stat mech essentially is an application of the saddle point method. Or its other cousin, which is more appropriate for real variables, is called the method of steepest descent. Okay. What I did right now is basically I use steepest descent to approximate the integral. When you're close to the peak, how fast do you come down? That depends on the overall scale. If the overall scale increases, and in stat mech it increases with the number of particles involved in the system. That is why when in the thermodynamic limit, when n goes to infinity, you simply have a system where all the contribution comes from the peak. And you have used this several times. For example, you have used it to explain why you can use, say, canonical and ensembled or microcanonical ensemble both to explain the same thermodynamics. Or, well, I can keep on going on and on about it, but basically, in many, many places in statistical mechanics, at least, you have used the steepest descent method without perhaps calling it the steepest descent method. But the basic idea is contribution comes only from near the peak. Now, the problem is that when you're dealing with a complex integral of the kind that we are, things are a bit more complicated for the simple reason that you cannot have a local maximum at least for the real part of the imaginary part of an analytic function. So you are forbidden from using that. But what you can do is you can try to remember, because of this freedom that you have of deforming the contour, C1 can be deformed into any shape you want as long as you start in the right sector, go to the right sector. Okay? And then, if you can choose your contour in such a way that the real part of the exponential changes the most rapidly, there can also show that there is a condition where the imaginary part will become stationary. And that is how you decide. Then what happens is contribution will come only from very, very close to that point, the so-called saddle point. And now you can use this deformed contour to give you very good approximations for the behavior of the function for large values of lambda. Now you might say there is no overall factor here. The integral that you have is something like this, the minus t cubed by 3 plus xt dt. But there's a very simple trick by which you can change this to an integrand which is an overall x. So I will leave you to worry about that change so that you can basically write this as e to the x times some function overall, some function which does not depend on x at all. You need to change the change the variables a bit for that. And then you can see that this integration can be evaluated using the steepest descent method, or in this case, in the complex plane, is called the saddle point method, by choosing your contour in such a way that it passes through, say, for positive x, there are these two saddle points. You can choose a contour which goes like this. Oops. Bad drawing, but okay. Let me just continue with the drawing. I want a contour which goes like this. Not quite what I want. With a contour which goes through this. Through this saddle point, straight up. And then you can get a contribution only from immediate vicinity of this region and use the kind of Gaussian formula that we derived. And from that, find out the asymptotic behavior. Okay. So is this point clear? But I really need to know how much complex analysis you know in order to understand this thoroughly, because this may not have been covered in your course before. I'm not saying this particular method. I'm just asking whether this kind of argument that you can move your contour anywhere and then you can choose your contour in such a way that the integration comes out to be easier to do and so on. Have you done this before? Yes? Is saddle point completely new to all of you? That's an important question. Is this a completely new thing? Because if it is, then maybe we'll need some more time to understand this, because this is very important. Okay, Rajrupa is saying yes, sir. The trouble is Which question are you saying yes, sir, to? This is completely new to all of you. Is that the question
Yes.
you're saying yes to?
Yes.
It's new. Okay, so maybe I will need to give you a more detailed description of this. Okay, okay, I may not be in a position to complete the description today, but let's give it a try, because it's going to take some time then. Suppose you have a function f, and let's move away from this specific function that we are talking about. We are talking about a general situation, a function f, a complex function. So of course, you know that you can write this as something which has a real part and an imaginary part. And the argument t, which is a complex number, can be written as, again, in terms of real and imaginary parts, x and iy. And of course, when you say contour, you really mean that x and y are both given as function of some common parameter tau. As tau changes, x changes and y changes, so you get a point which moves on the complex plane. So t, which is x plus iy, is actually parametrically defined by this parameter tau. As you change tau, you go along the contour. So Aniruddha says it was supposed to be taught in StatMech, but it wasn't. Well, in StatMech, what would have been taught is really not the saddle point approximation so much, not the complex version, which is what we will need, but the steepest descent approximation. That StatMech actually needs that more, but the two are very closely related. Okay, so let's just explore how the function f changes as you move along the curve, or rate of change of the function. Specifically, let's look at the rate of change of the real part of f. Let's say u. What is u dot? You know what it is, right? It's going to be del u del x times x dot plus del u del y times y dot, right? And this is, again, something which is pretty familiar to all of you. Take the gradient, in this case, a two-dimensional gradient of the function u, dotted with x dot, so you essentially get this result. So this is the rate at which the real part changes. Now, so first question, in which direction should you move to change so that the real part changes most rapidly? This has nothing to do with complex analysis, even. This is just a simple question from first year vector analysis. Which direction should you move so that the function changes most rapidly?
About the normal.
About the?
Normal to the function.
Normal to what?
The function at the point.
The function has no normal at a point.
So the normal to the function.
There is no normal to a function. I know that you, okay, I'm aware that you know what you're talking about. It's just that you're using a completely wrong word for it. So Ishida is saying cos theta is 1. Yeah. That is theta is 0. Or theta is pi would give you the steepest change in the other direction. It's not the normal to the function, it's actually along the gradient. When you say normal to the function, I guess you mean normal to the surfaces of constant values for the function. That is the same as the direction of the gradients. Right? So if you had surfaces drawn at constant u, in this case, because we are in 2 dimensions, those surfaces will be lines. Normal to those lines would be along the gradient, of course. But easier answer is just along the gradient, right? So if you move along rad u changes fastest. And if you move perpendicular to grad u, then u does not change, at least to first order, right? That's because cos theta will be 0 there. But now you all know that your two functions here, u and v, and the two functions are related like this. Del x u is what? Del yv. If it's an adic function, at least, that's what we are assuming for the time being. Del yu is minus del xv, right? Now, what does that tell you about grad u and grad v? These conditions. Yes? What is the condition between these two quantities? The gradient. Okay, my delta u and delta v, maybe I would better off be consistent. So instead of using the inverted delta triangles, let's use nablas. How are these two related? These are two vectors. They are perpendicular to each other, of course. This condition simply is the condition for perpendicularity of two vectors, right? So notice that if you are moving in a direction in which u changes most rapidly, then in that direction v doesn't change, at least to first order, and vice versa. Okay, so you can keep either the real part or the imaginary part at least stationary, if not completely fixed, but at least fixed to first order, and change the other component, either the imaginary part or the real part, depending on which way you're moving, most rapidly. Okay, so this is a basic geometric fact about analytic functions. In the direction in the complex plane in which the real part changes most rapidly, in that direction the imaginary part does not change to first order at all. And the same goes for the imaginary part vis-a-vis the real part. Okay. Now, if I manage to change the real part very, very rapidly, that is, you're close to a maximum. Remember, here what happens is grad u, of course, dictates the size, rate at which the thing is going to change, right? The gradient tells you how fast it is going to change. The bigger the gradient, the faster it is going to change, right? So if you want to figure out a situation where you get the maximum change, then what will you do? You will look at, when you are looking at u being at a peak, what will you do? You'll take grad u equal to 0. But if grad u equals 0, then this is 0, this is 0. It also tells you del yv and del xv is also 0. What that means is, at the point where you will have the maximum, f prime will vanish. That is, you are at a maximum of u, not a maximum of the function. Because the complex function has no maxima or a minima. But when you are at a maximum of u, the derivative of the function vanishes. Okay. And now what you can do is you can choose your direction of. Okay, now I'm going to give you a hint. This is something which you should try working out yourself. You're free to deform your contour any way you want, but including, for example, here. In this example, this contour C1 can be deformed any way you want, but if you can go through this point, that if the deformed contour goes through this point like this perhaps, then you might think that because you're going through the extremum of the real part, you are managing to find out a region where a small part of the curve will give you almost all the contribution. But there's a small catch there. The catch is, even though the function has peaked here, that is f prime is 0, that doesn't necessarily mean that that you are going to get the maximum change along any arbitrary direction. You have to choose to move in a very specific direction here. So this is something which you should be able to figure out just by writing down the integral. You deform the contour in such a way that you go through this point, but also go through in a very special direction. If you do that, then one part, the imaginary part, doesn't change at all. The real part changes very, very rapidly because you're at a peak and then you're coming down very rapidly. rapidly for large x at least, and therefore the Gaussian approximation gives you a very good approximation. So I will ask you all to think about this, because this will take some time for me to explain, but more importantly, this is something which you should try to figure out for yourselves, this particular part. So did you realize what I'm asking you to figure out? That is, one, this is an extremum point. It's nice if I could send the contour through this, but I want to send the contour through this in a particular direction. And if you can hit upon that, the good thing is then you need to really worry only about a small part of the contour near that peak to figure out what the approximate integral is going to be, because that part is going to contribute almost everything. The rest is going to contribute almost nothing. And then you're done. Then your integral works out right. Then the integral simply becomes a Gaussian integral which can easily evaluate. So your job is to figure out which direction should you cross the contour in general for an arbitrary function. Here, of course, for this particular function that you have, you should also figure out which direction you should cross this in. Okay, one place where you will find a rather nice description of this ID equations, integrals, and so on. There's a lecture video series on the net, and I'm pretty sure many of you know this. There's the Advanced Quantum Mechanics set from Barton Zweibach. In fact, our course and his course, this is in the MIT Open courseware. Our course and his course has quite a lot of overlap. Some of what I've talked about you can also find in his videos. Not all of them, but some of them. His description of this Wkb method, including the behavior of ID functions, is actually very, very nice. You should perhaps take a look at that if you find my descriptions difficult to understand. There's only one small catch. His final results are all correct, but there is an error in his asymptotic behavior analysis. So I will ask you, okay, this is an assignment actually, an open-ended assignment. It might take till the end of the semester to work out. Take a look at Barton Zweibach's MIT lecture for WKB and specifically for the Airy function asymptotics. I don't really want to give that's precisely why I'm not saying more about the direction, because you have to figure it out yourselves. It so happens that, okay, I wouldn't say he has made a mistake. All I would say is he sort of implied something. He didn't work the whole thing out. He, of course, left some parts for the students. But there he made a statement which sort of implies a wrong thing. So specifically about the behavior of the ID function asymptotics. Strictly speaking, he didn't make a mistake. He didn't say that. But from what he said, the only possible inference you could draw would be something like that. So homework for special points, anybody who can find it out, find out what exactly is there in this lecture which requires a bit of a correction, so to speak. You will get extra 5 points if you can find that out and explain what the correct thing will be. So we will discuss this in the next day, but in the meantime, I would prefer that all of you read up a bit on the complex analysis part, at least the Cauchy-Riemann conditions and the basic complex analysis theorems. Maybe not all proofs, but at least the basic things should be handy, because you will need that. Not only for this part, but also for scattering, which is going to come soon. Okay, so is the question clear? That is what the open-ended question that I've given you right now is the question clear to everybody? What I'm asking you to do? If the answer is neither a yes nor a no, then I'm in a bit of a trouble. Yes.
So could you repeat it once more?
No, all I'm saying is this. particular lecture, this is a wonderfully good lecture actually. You should definitely look this up. This whole series is very good, although some of it overlaps with our course, some of it doesn't. So if you want some extra reading, this is a really very good material. You should really take a look at this. What I'm saying is, when he describes the asymptotic behavior of ID functions, in fact, what was trying to do today, although I didn't reach the end, he talks about the saddle point method. He uses slightly different contour and slightly different convention from us because of just one thing. Because what he has done is, instead of taking e to the power zt x of t dt, which is what we did, he took e to the I z t. So basically, he took something which looks like the Fourier integral, although it's not over the real line from minus infinity to plus infinity, it's over some contour. And because he has taken it to the I z t, his t is essentially rotated through 90 degrees from our t, which means his diagram, so his diagram is essentially our diagram turned through by 90 degrees. So that if you imagine rotating this whole diagram here through 90 degrees by multiplication of an I, that's what multiplication by I does, right? It rotates to 90 degrees. Then you get his version. So if you want to match his version to ours, all you have to do is remember that instead of this minus 30 to plus 30, what he has is 60 to plus. So for him, it's essentially this region which is forbidden, and so on. So you have to sort of, so this whole thing turns around and there's a forbidden triangle up here. But that's simply a matter of just using a slightly different convention. And then he goes on and describes exactly this asymptotic behavior and everything using the saddle point method. But he makes a small, okay, I wouldn't call it a small mistake. He never makes the mistake because he never says it out loud. But he works out one part, the airy function AI's behavior. That's something which he explicitly works out. He does it perfectly correctly. No problems there. But when he mentions BI's behavior, he actually says something which is misleading. He doesn't carry through the full calculation, so you wouldn't call it a mistake. But he says that, okay, you are supposed to work out the behavior using a particular deformation of the contour. And in saying that, he doesn't say exactly the correct thing. Basically because he wasn't bothered about it. Basically because he already had got the result that he wanted. But what I would actually urge you to do is try to look at this particular lecture and try to spot exactly what was not quite correct in what he said and what would the correct thing have been. It's not important for the rest of the discussion for the simple reason that you could just take the result and work from there. You didn't have to go through the inner steps. But the important thing is, that will help you understand whether you have actually comprehended this method at all or not. So next day, I'm going to start with the saddle point method in general from complex analysis, to tell you what that is, how to use it, and quickly work out the saddle point approximations for this particular solution. Will you be giving recorded lectures on this part of the course? I don't understand. This is a recorded lecture, right? The lecture, this is recorded. What exactly do you mean? You mean a standalone lecture? That is not a discussion. Is that what you mean? Well, I won't, because that is precisely why I'm having this discussion. This part is more complicated than the rest. The rest is just basic mathematics. You could just follow it in a standalone lecture. This one I wanted to discuss with you, and which is why your feedback is important. I need to know whether I'm getting through at all or not. Okay. I am going to talk about airy. I'm going to talk about Wkb. I'm going to talk about airy functions, all of that. But all these mathematical details, this needs to be discussed. This part will not be there in the recorded lecture. For that, you have to either refer to this or work it out yourself. And the second option is, of course, better. So we will stop today because, frankly, in the time left, I will not be able to do justice to the method. So next day we will start with the saddle point method and talk about this particular specific mathematical part. And please take a look at VLearn. You already have 2 assignments now. One which is due on Sunday, the other which is a long-term assignment, which is due in 2 weeks. Okay, any questions about this? Yeah, you're right, because my laptop had actually crashed, so I couldn't do it earlier. I had to do it now. Okay, I will do it today. This one. You're right. I'm sorry about that. I couldn't upload the previous equation before this. I had actually deleted it from my drive. I had it only in my laptop, and until my laptop I got back my laptop, I couldn't do that. Sorry about that. Okay. Anyway, then bye for today.